All right, the lecture for today is going to be about mechanical equilibrium, and I'll do 3 videos, and hopefully this one will be short and easy. I always say that, and it's never true. But the first thing to know is the concept of stress, and hopefully you're all familiar with this. You have taken some uh, solid mechanics or elasticity class before. So the main definition is if you have a body and you cut it and you draw a free body diagram. Well, I guess I should do. So you cut the body in two and you draw a free body diagram. Then there's gonna be some, well, in the, so this is the normal, and then there's gonna be some force per unit area. Um, and that force per unit area is called a traction vector. So this has units of force per unit area. And it depends on the choice of normal defining that plane. And obviously on the point. Where exactly, I mean, this body has some other external forces. These are the same here. And then it also depends on which point you pick. So obviously we know that point has some coordinate x. And the main concept of the stress tensor is that actually the distraction vector depends linearly on this normal at a given point x. And so, yeah, what that means is that the traction vector depends linearly, so there's a tensor. I'll just state here, traction vector depends linearly on the choice of normal at point, and this should be at the form x at point little x. And therefore, because it depends linearly on the normal, then we can represent that relationship with a second order tensor. So this sigma is a second order tensor. That's the stress, Cauchy stress tensor, or true stress. Obviously in 3D, this can be represented as a set of components forming a 3x3 matrix, or in 2D, a 2x2 matrix. What else should I say about this stress tensor? Not much to say. It is a tensor. It transforms like all tensors. It can be expressed in a basis. So yeah, it looks like a matrix. It's a symmetric matrix. I'm not gonna show why it's a symmetric matrix, but it's because it satisfies angular momentum balance. But let's go directly into the linear momentum balance. But there's, I guess, the only thing that I want to point out here is that there is a stress tensor sigma, which basically tells you how force per unit area inside of the material would look like if you were to do this type of free body diagram, and if you cut in a particular orientation at a particular point, that sigma tells you basically the reaction force or the internal force. So that's the stress tensor. I guess the other thing that I would like to say, because it will come up later on, is that this tensor is associated with the deformed configuration. And this just keep in the back of your head, because in the previous lectures where I've described different tensors to describe strain, to describe deformation, the even vector fields like the velocity and the acceleration that we can describe in the reference or the deformed configuration. This tensor, the Cauchy stress tensor, it's associated with the deformed configuration or current configuration. And just keep in the back of your mind, because as you can probably guess, we can have things that are related to stress that are defined with respect to the reference configuration. And I think hopefully the homework 2 that has some problems on the velocity and acceleration plotted in the reference or the deform will give you some idea. So there's gonna be again some notion of stress in the reference, but this one is defining the deformed configuration, which is the sort of the observed configuration. This is what you see. This B configuration or deformed configuration is what you see. So let's go into linear momentum balance. And you probably know this one already, but if you don't know, then we have the body here. It has some Dirichlet boundary conditions or applied displacements. You have some tractions at some part of the boundary. Again, this is the body B. And then the boundary we're gonna call omega is the boundary of B. So there's some region that has some Dirichlet boundary condition. There's some region that has or the applied displacements essentially. There's some other part of the boundary that has traction boundary conditions. I'm gonna call it gamma T. So gamma and the total boundary is the sum of these two boundaries. And the equilibrium is going to be, at least the linear equilibrium is, if you integrate all those forces applied to the body over the boundary, and you consider there might be some body force field. Let's call that B. So B is a body force field. Then let's say B and so the that should be in equilibrium, right? So the sum of the applied external forces plus the sum of the body forces should add up to 0. And that's the linear momentum balance. And again, we're not gonna really go into the angular momentum balance. That gives you the symmetry of the stress tensor, but we're not really gonna go a lot into that. Okay, so we have the linear momentum balance, and we're gonna apply this traction right here. It's related to the stress, like we said before. So this is the stress times the normal. Plus the integral of the body force, and that gives you the 0 vector. And if you go back to some of the mathematical preliminaries, we're gonna essentially use one of the integration theorems that we had before to transform this integral into a volume integral, to turn this boundary integral into volume integral. So again, this is the linear momentum balance, which is basically sum of the forces equals 0. So if you sum up all the tractions at the boundary plus body forces, you should add up to 0 for the system to be in equilibrium. So I'm ignoring dynamics for now. And then I'm gonna, if I use Gauss theorem, I can transform this boundary integral into a volume integral. So this is gonna give you divergence of sigma plus this body force field equals 0. And this actually you could do for any sub-region of the material, because you don't have to isolate just the tractions in the outer boundary. You can draw any closed region of the material, and you could do the same, because once you do the free body diagram like we were doing here, you will get the same thing, right? So if you do a free body diagram for this, for part of the material, then you will have, let me call this another letter A. So in that domain A, we could do the same. So we could have the tractions applied to that boundary, right? Plus boundary of, I should, instead of gamma, let me use boundary of A plus the body force over A, dB will equal 0. Because this is, if you remember any sort of statics classes that you have done, you can always do a free body diagram for any sub part of the system. So this would lead to sort of the same type of statement, where we will have an integral over A of divergence of sigma plus V dV equals 0. So because this can be done for any sub-region, we can arrive at this is called localization. And you end up with this. This is your equilibrium equation, which is the divergence of sigma plus the body force equals 0 if you are ignoring accelerations. And hopefully you were familiar with this before, but if not, then now you know that this is the statement for mechanical equilibrium. And then what we're gonna do with this is so this is sort of called the strong form of the equilibrium. It's part of the strong form. So we're gonna do strong form and weak form of equilibrium. And the only thing that I'm gonna, before I do this strong form and weak form of equilibrium, the one thing that I'm gonna say is angular momentum balance essentially leads to the symmetry of the stress tensor. And I'm not gonna do the derivation. So that's it. So that's basically the two things that you get from equilibrium is the divergence of sigma plus the body force equals 0 at any point x, and also that the stress is symmetric. And now in reality, you never solve that PDE. So the strong form of the equilibrium problem, static equilibrium problem, would be to find. So usually the stress is related to the displacement field, and you would say, find the displacement field, for example, such that this equation is satisfied for some boundary conditions that I was stating here before. But typically you don't solve that because this requires second order derivatives. You have divergence of sigma, and sigma will be related to the strains, so it will be a function of these first derivatives of the displacements. So you will end up with second derivatives, and that's not that easy to work with. So you want to reduce the degree of continuity that you need. And for the mechanical equilibrium problem, that can be done by it's either the weak form of equilibrium, or it's also very commonly presented as the virtual work statement. And that's actually what gets coded, or principle of virtual work, I guess that's the correct wording. And that is what is actually solved with the finite element. So we have this again. We start from this statement, the local statement, but we're gonna go back to the global statement. So we have, integral over our domain of this guy equals 0. And then what we're gonna do is we're gonna multiply by a weighting function. And so this is typically what you would do in the in the finite element framework. So again, I'm starting from, so if this is 0, then the integral for every point x, then the integral will be 0. But I want to do something such that it's gonna reduce the continuity. So I'm gonna multiply by a test function. And this is called the principle of virtual work because this is a virtual velocity. So I'm gonna contract this vector with this virtual velocity field. So again, if this is 0, then it doesn't matter if I integrate it and multiply by some arbitrary function, because this delta v is an arbitrary function. Then what I'm saying is that this has to be 0, right? As long as this is 0, then the product with this arbitrary function should be 0, because this has to be satisfied basically for every or any virtual velocity that you want to pick. So in the case of solid mechanics, this is typically called the principle of virtual work. More generally, it's just a variational statement or a weak statement, because we have a residual, and then what you do is you multiply by a test function. This is also called a test function or a weighting function, and integrate. And then we want that to be 0. And so it's weaker, and we'll see why it is weaker, because we can do sort of integration by parts. Or the equivalent of integration by parts in the I think it's Gauss theorem or Green's theorem. I should check this. And we're gonna split again into some integrals over the boundary and some integrals over the domain. And in particular, what we're gonna do with this divergence is we're gonna take one of those derivatives and sort of pass it to this weighting function. So we're gonna end up with so if you recall sort of your integration by parts formula, this is gonna end up with sigma contracted with the gradient of this virtual velocity field, and then plus, and then we're gonna end up with an integral over the boundary for this is the traction basically at the boundary and at the boundary, at the part of the boundary that has tractions. There's some requirements for the virtual velocity field. So I guess I'm being a little bit hand wavy here, because this is not particularly the crux of the course, but the virtual velocity field has to satisfy something. It's not completely arbitrary. It has to satisfy that it vanishes at the wherever you have imposed displacements. So then we have the integral of the virtual velocity field only over the region that has traction boundary conditions. And here we have dv dotted with b. And that equals 0. And notice that what we have done here is we have passed one of the derivatives, so the divergence, which entails a derivative on the stress, we have sort of passed that to this virtual velocity field. So now we want basically this for all delta v. So we still want this to be satisfied for all delta v. But now this is a weaker statement because we passed one of the derivatives that was in sigma, we sort of pass it to the virtual velocity field. And then we can do something even a little bit more, which is that because the sigma is symmetric, then when you contract the symmetric tensor with a skew symmetric tensor, you get 0. And so the gradient of the velocity field, or some arbitrary vector field, you could have a complete it has a symmetric part and a skew symmetric part, and the skew symmetric part, when it gets contracted with the sigma, vanishes. So really the only thing that you should care about is the symmetric part. So this guy has a symmetric and a skew symmetric part. And the skew symmetric part vanishes when contracted with a symmetric tensor. So skew symmetric double dotted with symmetric tensor equals 0. So then the only thing that I need is the symmetric part. And the symmetric part of the virtual velocity gradient is this guy. Because if you remember, the gradient of the velocity field was L, right, which was the spatial gradient of the velocity field that I defined in the last video. And then the symmetric part we called D. And so this is sort of a virtual D, or delta D. And it's sort of like a virtual strain. And that's it. So this is the weak statement, which is essentially find. So this sigma is a function of the displacements. So you want to find u such that, well, find u restricted to satisfying essential boundary conditions. Essential boundary conditions, or Dirichlet boundary conditions, or displacement boundary conditions, however you want to call them, is the same. Find u satisfying essential boundary conditions such that this is true for all delta v vanishing at the boundary with essential boundary conditions. And then just a couple of notes. This delta D is essentially the gradient of delta V plus the gradient of delta V transpose half of that, and sigma is a function of u, right? And there's some essential boundary conditions. I'm not really stating them too rigorously, and then there's some natural boundary conditions which are here. So this, and maybe I should also make a note. T on gamma t are natural boundary conditions. Natural boundary conditions. And that's the weak form of the linear or the mechanical equilibrium. As I said, the angular momentum balance just leads to the symmetry of the stress, and linear momentum balance leads to the statement above, which was this. But when you multiply by a weighting function and integrate, and you do sort of the integration by parts for 3D, then rearrange things a little bit, and you call these weighting functions virtual velocities or virtual displacements, then you end up with what it's called either the principle of virtual work or just the weak form of mechanical equilibrium. Either one would be fine, and that's the statement, and that's essentially what gets solved with the FE. So FE solves this. It doesn't solve directly the strong form. So it doesn't directly solve this equation. It solves this integral form. And I could discuss more about that in lecture. For now, I'll leave it there. And the other thing that I would say is this is a general way of transforming PDEs into these integral statements. It's not really the purpose of this course, but I could dive more into this if you want. Go a little bit more into just more exercises or more examples of strong form to weak form. But for now, just take this as this is the statement that basically we're gonna solve, and it's called principle of virtual work or the weak form of mechanical equilibrium. Alright, so that's it for this video. Then the next video is about the different